All right, so now let's look at the ideal Brayton cycle. Brayton cycle was developed in the 1870s as an idealization of the way a simple gas turbine could operate. So it really becomes a four-step cycle where we bring in air from the outside, we compress it to a high pressure, goes into a combustion chamber where heat input via combustion occurs. Now this very high pressure, high temperature gas goes into a turbine where it produces power. Generally they're sort of built so that the compressor and turbine are all on a similar shaft so that the turbine can drive the compressor, and then any extra power output can be used to create electricity or power something directly. And then we exhaust the material to the surroundings. So my last process is heat exchange to the outside. It's really exhaust and intake of air. And so that's why I drew this process as a cloud. It's just going to the surroundings. So I have the processes 1 to 2, 2 to 3, 3 to 4, and then 4 to 1 so that I can have it as a four-step cycle. Now, the cycle is really, in many respects, so much like the Rankine cycle, but I have a gas, so I have a compressor instead of a pump to get it to high pressure. I have a combustion chamber instead of a boiler or a steam generator to produce my hot, high-temperature product, and then I'm going to produce power through a turbine, and then I'm going to have some sort of cooling process. So in so many respects, this is like the Rankine cycle, but I never have phase change. So if I look at that 1 to 2, my compressor is ideally going to be reversible and adiabatic. It's going to be a compression phase. So if I do that, the pressure is going to go up. The entropy, if it's reversible and adiabatic, will stay the same. So the temperature should also go up somewhat. Pressure will go up a lot. In the second, this is my combustion phase. It's a heating process. Okay, yeah, there's a fire. Okay, combustion happens. But I can treat it as if it were isobaric heat input, much the same as how I did the boiler. And so it's going to be a constant pressure process. Volume will change as it gets heated, but it's constant pressure. And the entropy will change and the temperature will go up. I can't have isothermal here like I sometimes could with the Rankine, but that was only because I had the phase change happening. So I will always have a temperature increase from 2 to 3. Now I'm going to go through that turbine. So that's going to allow the stuff to expand to a lower pressure. So it's going to drop the pressure and increase the volume. It's expanding. It's reversible and adiabatic, so there's no entropy change. And then finally, I'm going to cool this by releasing stuff to the atmosphere and bringing in fresh stuff from the atmosphere. Since it's all at the same pressure, an assumption of isobaric cooling is good. So I'll go from 4 to 1 at a constant pressure. And I'll have both temperature cooling and entropy decreasing during this time. If I have no change in kinetic or potential energy, then I can use my form of the first law, this very simple form. Q is W plus HE minus HI to analyze each one of my steps. So in this one where I have no heat transfer, adiabatic, right, then I'm going to have W is HI minus HE. If I have heating without work, then Q is HE minus HI, and so forth. So the analysis is going to feel very similar to what we had with the Rankine cycle, just losing that phase change. So looking at properties will be different. If I look at the specifics, work input happens in steps 1 to 2. That's what compression is. It requires power. Work output happens in steps 3 to 4. Okay, that's the turbine. Usually we analyze them sort of jointly because they really are turning jointly. So in that case, the work from 1 to 2 plus the work to 3 to 4 is my net work. Remember from the first law, it's going to be enthalpy in minus out. So for the compressor, in is 1, out is 2. For the turbine, in is 3, out is 4. Add those together. That will get me my net work. Heat transfer happens during that combustion phase. So that's the enthalpy change from 2 to 3. So H3 minus H2. And if I need the thermal efficiency, it's the net work over the heat transfer in, and so I get this. So no problem. Let's look at how I can come up with all of those enthalpies, because this is not new. This is really what we were doing for a basic Rankine cycle. Difference is, how do I gather the data for these values of H? So let's talk about air standard. If I have air standard, then, okay, 1 to 2 is isentropic, but it's an isentropic ideal gas. So I can use delta S equals 0 and the formulas, or the easiest thing to do is I usually know how much I am compressing the gas, so I know how much larger P2 is than P1. Frequently it's even called the pressure ratio, simply meaning it's from the high pressure to the low pressure. What's the ratio of those? P2 over P1. And for isentropic processes, I can say it's equal to PR2 over PR1. These numbers I read out of the tables based on temperature. Relates to the pressure through this equation. For isobaric, usually I have no problem there with getting the information because it's constant pressure. The other one that is a problem is the isentropic expansion of the turbine step. And so now the pressure is going to drop. But if you go back and recall, I had that it drops exactly the same amount. So increased from P1 to P2, now it's going to decrease from that pressure to the new pressure. Oh, wrong slide. Sorry about that. And so P4 over P3 will be the reciprocal of that pressure ratio. But again, I can use that P sub R table to relate temperatures to pressures and come up with the data. As you're working problems, sometimes it's nice to have a feel for what would be a reasonable value that you would see if you were really to build something that was based on a Brayton cycle. And typically what you're going to find is that these pressure ratios will be on the order of 5 to maybe 19 or 20. So 5 to 19 is kind of considered a typical set of values for these. You could build them to something huskier than 19, but usually the cost of the construction makes it non-practical. And you don't get enough power out to justify building one for a pressure ratio less than 5. So these numbers, as we see, will be the sorts of things that we will encounter as we start working problems. Now, what if I had cold air standard rather than air standard? Well, again, I need to use the cold air standard rules. First of all, delta H is Cp times delta T. Remember, I'm using constant C sub P. So everywhere I had a delta H, I can put in a Cp delta T. Cp's are going to be the same, so I end up with formulas that start looking like ratios of temperatures. Okay? So that's one thing that's interesting to note. Another is, as I go through those isentropic processes, these are going to be for a reversible and adiabatic or isentropic ideal gas process with constant C sub P. That turns out to be a special polytropic process. Now you recall polytropic processes, they were those ones where you had PV to some power as constant. And this is the one, it seems like such a weird case, but the power is K, which is the ratio of C sub P over C sub V. And it's something that we can look up in those tables. So the pressure ratio, P2 over P1, the high over the low pressure, is going to describe for me the ratio of the temperatures from T1 to T2 if I take those to the k over k minus 1 power. And I'm not going to prove that. It was back in one of the earlier chapters from Thermo 1. It's a polytropic process result that we had obtained back then. And my other polytropic isentropic process is from 3 to 4, and so I can use a similar sort of thing for that one. One of the things that's really interesting, though, is if you chase the algebra, if you solve this for the T1s and T2s in terms of R sub P and plug all those numbers in here, turns out that if you take that pressure ratio to the 1 minus k power over k, then that really is the exact same thing as this formula up here. Okay? Now, it's not true for air standard, but for cold air standard, I can simplify the math, and the pressure ratio to the 1 minus for air, 1.4 is typically the value we use. So 1 minus 1.4, so negative 0.4 over 1.4. And all I need is the pressure ratio, and I can approximate the thermal efficiency. Now this is handy because even if I'm assuming air standard, I frequently will check my work by using this formula to see if my thermal efficiency is close to this. It's a very easy way to evaluate your work without too much effort. All I need is the pressure ratio and K for air of approximately 1.4. So in the next video, we're going to do an example using the Brayton cycle.